All right, so let's go ahead and get started here. Problem 1. Elaine gets quiz grades of 90, 83, 64. She gets a 69 on her final exam. Find the weighted mean if the quizzes each count for 20% and final exam counts for 40% of the grade. Okay, so this is a weighted mean problem. Okay, weighted mean. All right, so what we want to do here is create a table of your x values and your weights. And what are we talking about here? What is the thing that we're averaging? We're averaging all the grades, right? So we have the scores here. I guess we have the grades, scores. And then the weights here. In this particular case, they're giving it to you in percentages. It doesn't necessarily have to be in percentages. For example, if you're doing like a GPA, the weights in that case would be like the units per class, right? There, you don't have percentages associated with your classes. But in this case, it is percentages. All right, so what types of grades do we have? Well, we have quizzes and we have a final exam. So I guess we have 3 quizzes, Q1, Q2, Q3, and then we have a final. And the grades that this person got on the quizzes were 90, 83, 64, and then a 69 on the final. Now each quiz was worth 20% and the final was worth 40%. And to calculate the weighted mean, well, that is done in this fashion. That is the sum of each grade, each score, times its weight divided by the sum of the weights. Okay, now you could actually put this in L1 and L2 and do 1-var stats, right? This would be your frequency list. And you just do 1-var stat L1, L2 if you were using a TI-83. On the TI-84s, it'll just ask for your list and then your frequency list. So that's what you would have to do. I'm not going to do that here. We're just going to do it by hand here. You get each score 90 times 0.2 plus 83 times 0.2, 64 times 0.2, and 69 times 0.4. And you just add them all up. Okay, that's the numerator, and the denominator, we're just summing up all the weights. So the weights are that second column. Now in the case that you're using percentages here, like we are, all the weights should add up to 1. Okay, again, the weights don't necessarily have to be percentages. They can be, but they just don't necessarily have to be. Okay, so if we were to actually add that up, multiply and add that up, we will get 1 down here, 75 in the numerator once it's all said and done. Therefore, your average grade is a 75. Number 2 is also exam 1 material. This is where we drew a box plot for a list of data. The nice thing about this data is it's all sorted from least to greatest. So it's easy to identify the 5-number summary, which is the first thing we need to come up with. And then after that, we need to come up with the fences. That's the lower fence and upper fence. The purpose of that is to identify any outliers. And then finally, we're going to go ahead and have some sort of visual depiction of this by using a box plot. We'll start with the 5-number summary. We have a minimum, Q1, Q2, Q3 maximum. The second quartile is also known as the median. The first numbers that you can identify very easily from the very beginning is just the minimum and the maximum. Since this is sorted from least to greatest, the minimum was 154 and the maximum is 275. Okay. The next step here, the next easiest one to identify, is the second quartile. Now, in this particular case, we have 30 numbers, right? And these quartiles may be one of these numbers. It might lie between 2 numbers. You have to be very careful. Okay, every case is different. Okay, so just make sure you're doing this correctly. How do you find the median? Well, the median is the number that splits the data set into 2 equal parts. The fact that we have 30 individuals here, well, 30 divided by 2 is 15, right? So we have 15 and 15. So that means our median is actually going to lie between the 15th and the 16th. Okay, so let's go ahead and count that. So the first row is 10, right? And then we have 11, 12, 13, 14, 15. I know you can't see my cursor, but this is the 15th one, and this is the 16th one. So the second quartile is right there. Okay, so in order to calculate that, you have to actually add those two numbers, the 15th and the 16th values, and divide it by 2. Okay. When you add those up, you get 196.5. Okay, so that's the second quartile. Okay, now the first and the third quartile, you can think of it, and in actuality, the math is done the same way, as the median of the first half. That's what the first quartile is. And then the third quartile is the median of the second half. Okay, so how many numbers do we have in the first half? Well, we have 15. Well, that's an odd number. Okay, if you split an odd number in half, you'll get, in this particular case, 7.5. So it should be the 8th value. Okay, that way it splits it off as 7 before that number and 7 above that number. So the 8th one will be the first quartile. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, and this just that's the first quartile. And just so that you can kind of see what I'm talking about here, I'm just going to highlight and then erase this. So for 1, 2, 3, 4, 5, 6, 7. And above that, we have 1, 2, 3, 4, 5, 6, 7. So that means 180 is the value that splits that bottom half into 2 equal parts. And then the same thing for the third quartile. Now starting with the second half, so ignore the first half. We're going to count from 198, as you can see here, onto the 8th one. So 1, 2, 3, 4, 5, 6, 7, 8. So I find this to be the third quartile. Again, let me go ahead and highlight everything and count that there's 7 before that and 7 after that. 1, 2, 3, 4, 5, 6, 7. And then 1, 2, 3, 4, 5, 6, 7. Okay, so that's definitely the third quartile. All right, so that's part A. Part B is to come up with the fences. But in order to come up with the fences, well, there's a formula for that, right? The fences require what's called an inner quartile range. That's just the range of the middle 50%. Okay, so inner quartile range, IQR, and that's Q3 minus Q1. That's how it's defined to be. In our case, Q3 is 211, and Q1 is 180. And if you take that difference, we get 31. Okay. We have a lower fence, and the formula for that is we start with Q1, and we're subtracting off 1.5 times IQR. Okay, well, Q1 is 180, right? 1.5 is just 1.5. IQR is what we just calculated right there, 31. And when we multiply the cell and then subtract that from 80, again, you have to follow the order of operations. You don't want to subtract first and then multiply. That's one of the most common mistakes I see. You should get 133.5. Okay, if you don't get that, that means you put these numbers in your calculator in the wrong order. Upper fence, we have the third quartile plus 1.5 times IQR. Again, your third quartile here is 211. Again, this one has the plus as opposed to the lower fence having the minus. 1.5 times IQR, which is 31. Okay, if you run that through your calculator, you get 257.5. Okay, these are the fences. Okay, so what do these fences do? Well, this is a way to essentially identify any outlier. So any value that's lower than the lower fence will be an outlier, and any value that's higher than the upper fence will be an outlier also, right? So they're just far enough from the rest of the pack to be considered not like the others. Okay, so in our case, do we have any outliers? Well, on the lower side, do we have anything that's less than 133.5? Well, no. The lowest that I see is 154, which is our minimum, right? Okay, so nothing on the low side. What about on the upper side? Well, anything over 157.5? Well, yeah, because our maximum here of 275 is higher than 257.5. So that's large enough or further away from the pack to can be considered an outlier. Okay, so we have, yes, 275. Okay, now we're going to go ahead and construct our modified box plot. The word modified is just one in which we censor out the outliers. Okay, if it was just to ask for box plot, then it would you don't have to do any of the censoring. Okay, but so we're going to use a modified box plot here. You always want to come up with a kind of like a measuring stick, right? Some sort of metric. So what I do is I look at my 5-number summary in addition to my lower and upper fence and figure out what's my lowest value that I see of all these numbers. 133.5 seems to be the smallest. That's our lower fence, right, of all the 7 numbers. And the very highest number that I see is the maximum, right? That's actually higher than the upper fence. Okay, so I want to make sure that I encompass this entire range. So from 133.5 all the way to 275. And you kind of want to use some nice round numbers to make your life a little bit easier. I'm going to go with from 100 to 300. That should be fine. I mean, I'm going to have a little bit of gaps in the at the far left and the far right, but that's fine. Okay, so I'm going to create my measuring stick here. And I'm going to say this is 100. This would be 300. Okay. At the very center here, it should be 200. Okay, and then I can keep on breaking it up. The more partitions that you have on your scale here, the more accurate box plot's going to be. I could break it up into 10s, but I feel like that's going to be a little too cluttered. I'll break it up into 25s. Yeah, that should be fine. It won't be too off. All right, so let's go ahead and start off with the fences here. 133.5, I'm just going to try to eyeball it the best I can. That's between 125 and 150. It's a little bit closer to 125. I'm going to go ahead and say it's like somewhere around like right there. I'm going to go ahead and label that. And 157.5 is our upper fence. That's between 250 and 275, a little bit closer to the 250, so somewhere around there. Okay, outlier 275. It's actually exactly right there, 275. Okay, now let's start with the box plot. That inner box is just the first quartile, second quartile, and third quartile, right? So the first quartile is 180, second is 196.5, and the third quartile is 211. So if I'm kind of try to eyeball it, 180 is between 175 and 200, a little bit closer to, well, a lot more closer to 175 than 200. So I would say, there's 180. I'm going to go with the third quartile, 211. Here's 200, 211. I would say maybe somewhere around here. And then 196.5. I'm going to go with maybe around here. Okay. And then we have to come up with what's called the whiskers, and that's going to identify the minimum and the maximum. Well, if you recall, the maximum was actually censored out. Okay. So what we have to do is, in order to come up with a new maximum, we have to just find the one that's next in line. So if I go back to this data set here, here is the maximum. The next in line that's still less than the upper fence is 255. Now that doesn't change our 5-number summary. Our 5-number summary is unchanged, but the box plot, since this is a modified one, we're going to have to identify that one. So 255. That's actually really, that was almost an outlier. It's actually way out here, 255, and that's just a line that hits the box. And on the lower end, 154, that was the minimum here. I would say that's like right here. And that is a complete modified box plot for this data set. Okay, next problem. Find the indicated probability, round to 3 decimal places, hint, binomial distribution. Okay, so this is a binomial distribution problem. Again, this is a exam 2 type of problem here. In a certain college, 33% of physics majors belong to ethnic minorities. If 10 students are selected at random from the physics majors, what is the probability that no more than 6 belong to an ethnic minority? Okay, so we have a whole pool of physics majors, and apparently at this college, 33% of them belong to ethnic minorities. And if you were to choose just 10 out of these, out of the entire pool, which is our sample right there, there's a certain probability that some will be from ethnic minorities and some will not. And the question is, what is the probability that no more than 6 belong to ethnic minorities? So to be no more than 6 means to be less than or equal to 6, right? Okay, so let me just kind of recap some of the criteria for binomial, okay, because the hint indicated this is a binomial, but let's just see if that's the case. If you recall, there are 4 criteria for something to be a binomial random variable, and that is, do we have a fixed number of trials? That's n. 2, each trial has 2 outcomes, so 2 outcomes per trial. 3, independent trials. And then 4, the probability of success is the same in each trial. Probability of success is the same each trial. And we call that P, right? So those are the parameters that we are looking for when we deal with these problems. We want to know what the n is and what the p is. Okay, let's go ahead and define our random variable. So let's go ahead and let, I'll call it x. That's typically the variable that we use. Let x be the what? Well, let's read that highlighted statement. What's the probability that no more than 6 belong to an ethnic minority? Okay, so it's the number of ethnic minorities chosen out of 10, right? So you can have 0 all the way up to 10, right? So it's the number of ethnic minorities out of 10. Okay, and the problem here is asking, what's the probability that there's no more than 6? To be no more than 6 is the same as less than or equal to 6, right? You can't be more than 6, but you can be 6. And x is less than or equal to 6. Okay. What's our n and what is our p? Well, our sample here is we take 10 students at random, right? That's going to be 10. And the probability that we successfully identified someone as being from an ethnic minority, well, they told us that's 33%. Okay, so that's just the setup here. And the probability that x is less than or equal to 6. Now, if you recall from the lesson on binomials, this particular one, when it's less than or equal to, this is actually found right in your calculator. This is just binom CDF. Okay, and go ahead and review all the different variations when probability of x is equal to a certain number, less than a certain number, greater than a certain number, less than or equal to, greater than or equal to. Review all those. Okay, that's all possibly on the exam. So n, p, x are the inputs here. Our n is 10. Probability of success is 33, and the x that we're interested in is 6. And if you recall what this does, if you have a discrete probability distribution here, this essentially just, we know that x runs from 0, 1, 2, 3, 4, 5, 6, 7, 8, I can't fit it, all the way up to 10, right? Okay, and what we're interested in is what's the probability that's less than or equal to 6? So that includes 0 through 6. We want all that. That's probability that x is less than or equal to 6. So we're excluding 7 through 10. Okay, if you just run this through your calculator, you will get 0.981. I believe they wanted 3 decimal places. Number 4, assume women's heights are normally distributed with a mean of 63.6 inches and a standard deviation of 2.5 inches. Okay. If 90 women are randomly selected, find the probability that they have a mean height between 62.9 inches and 64.0 inches. Okay, so they are interested in finding the probability that the mean height of these 90 randomly selected women is between 62.9 and 64 inches. Okay, so we're not interested in the probability of a single person, a single woman, being between those two values, but we're interested in the mean of 90 women. So if you recall, this has to deal with the central limit theorem. This is central limit theorem. Central limit theorem. And that's really just the mathematics behind the fact that we can predict the behavior of groups on average, or in this case, the mean height of 90 women, with more precision than we can for an individual, right? An individual has more variation in its height, right? If you just randomly select one individual from a group, rather than getting a group of 90 from a larger population, right? So that's what the idea behind this. So if we're looking for the mean height, let's start off with just defining what x is, okay? So x is the height of one woman, and we know that this is normally distributed because they told us, right? So that means x is normally distributed, where the mean is equal to 63.6, that's what they told us, and the standard deviation is 2.5. Okay? Again, we're not interested in that, but we do want to start off with that population distribution first. And then we go into the sampling distribution. So this, again, this is the population distribution. And then we're going to go into the sampling distribution. So we're going to let x bar be not the height, but the mean height of not just one woman, but of 90 women. And this mean height is our sampling distribution. And it's distributed normally because the population distribution was also normal. Okay. Now, if the population distribution was unknown, then the sampling distribution will still be normal because the sample is greater than 30. It's actually 90. Okay. Go ahead and review the notes on that for more of an in-depth explanation. So we know this is normal. Mu is target. Mu of the sampling distribution is the same thing as mu from the population distribution, which is 63.6. Right, these numbers match. However, the standard deviation of the sampling distribution of x bar is equal to the population distribution divided by the square root of the sample size, n. Okay, so in our case, sigma is 2.5, right? That comes from here. And our sample size, n, is 90. Okay. All right, so this is just all the setup here. Okay, now we can actually answer the question here. Find the probability that they have a mean height between 62.9 and 64 inches. Okay, so when dealing with normal distributions, you always want to draw some sort of picture, some bell shape. And the mean here is 63.6. These are x bar values. And the what we're interested in here is between 62.9 and 64 inches. So 62.9, here's 63.6. I guess 64 would be closer. I would say that's 64, and 62.9 would probably be a little further away. Okay, now these aren't probably drawn completely to scale. And we're interested in this area in between these two numbers. To find areas underneath the normal distribution, we use normal CDF. We have a lower bound, or upper. We need to identify the mean and the standard deviation. Okay, we're talking about the sampling distribution, so it's the standard deviation of the sampling distribution, which is that thing right there. All right, so the lower bound of our shaded region here is 62.9. Upper is 64. The mean here is 63.6. And the standard deviation is 2.5 divided by square root 90. Okay, you can put it in your calculator just like that. Of course, this is found under the distributions menu, and look for this function, normal CDF. You'll never use normal PDF. You're always going to use normal CDF. So go ahead and find that. We've done this many times. I'll go ahead and go into the lesson where we learned this and the details how to navigate your calculator for this. But it should look something like this. This is 0.9315. Okay, next problem. Use a given degree of confidence and sample data to construct the confidence interval for the population proportion P. Note, on the exam, be prepared for a confidence interval on proportions, means, or standard deviations. All right, so this particular one is on a proportion. And let's go ahead and see what's going on here. Of 346 items tested, 12 are found to be defective. Construct a 99% confidence interval for the proportion of all such items that are defective. Okay. All right, so it looks like we're looking at the proportion, right? And for confidence intervals, we're looking for some lower bound and some upper bound for this true population proportion. And that lower bound is your sample proportion minus some sort of margin of error. And your upper bound is that same sample proportion plus a margin of error. Okay, now there's a formula for this, of course. That's p hat minus the z-score, which is a critical value here. That corresponds to the level of confidence that we want, times the standard deviation of p hat, which is actually called the standard error, but it's this formula here. Now, you can actually calculate this by hand, just by plugging in all these values. We're going to have to figure out what they are. But we can also just use a calculator function, which is called one prop z-test. All right, so let's just go down the list here. So p hat is equal to x over n. That's your sample proportion. So that means we need an x and we need an n. Well, the number of items that we're testing in our sample is 346. And of those that are defective, right, because we're looking for the proportion that are defective, there are 12 that are defective. Okay, so that's what p hat is. So far we have p hat. We just need to know what z alpha over 2 is, and we know what n is, 346. Now this comes from your confidence level. Okay, so a confidence level of 99% corresponds to a z-score here, 2.576. Some textbooks use 2.575, but this is actually the most correct version of it. So you can plug all these values into this formula, but my preferred choice is to use one prop z interval. Of course, that's for proportions. All right, so if you run this through your calculator, and the inputs for your calculator would have to be x, n, and confidence level, and you would put in 12, 346, and for confidence level, you need to put that in as a decimal. And your lower bound will, in rounding to 5 decimal places, let's just say that, 0.00934 and 0.06002. So we say we are 99% confident that the true population proportion of defective items is somewhere between That's less than 1% right there, and about 6%. Okay. All right, next problem. This is a hypothesis test on one population. It could be a proportion, a mean, a standard deviation, variance. You're going to have to look for keywords to determine whether it's a proportion, mean, or standard deviation. And we've done plenty of examples that you can review on your own to test for that. The health of employees is monitored by periodically weighing them in. A sample of 54 employees has a mean weight of 183.9 pounds and a standard deviation of 50.1 pounds. Use a 10% significance level to test the claim that the population mean of all such employees' weights is less than 200 pounds. Okay, where's the claim statement? That's the first thing we want to identify. It's usually at the beginning or at the end, sometimes followed by the word claim, not always, but in our case it says, test the claim that the population mean of all such employees' weights is less than 200 pounds. Yep, we're talking about a mean here, population mean. So let's start where we always start, and that is step 1. Hypothesis statements. We are talking about a mean, so we got to use mu. The null hypothesis is always a statement of equality. And the claim statement here is that all such employees' weights is less than 200 pounds. So that looks like it's mu is less than 200 pounds in the alternative. That matches up with the claim statement. And the null hypothesis is 200. These numbers do have to match. Okay, step 2 is our significance level. Identify where that is. Yeah, it looks like it's 10%. Three is our test stat. Okay, and this is going to be a z-score. Of course, there's a formula associated with this, and that formula is our sample mean minus mu over the sample standard deviation over the square root of n. So that's a complex fraction there. And remember that this comes from our sample data, and this comes from the null hypothesis, right? And let's go ahead and list that out here, because this is what the calculator is going to want from us. Population mean, or the mean from the null hypothesis, our sample mean, sample standard deviation, sample size. Okay, the mu from the null hypothesis is right there, step 1, 200. Sample mean, I believe they tell us that, this sample has a mean weight of 183.9 pounds with a standard deviation of 50.1. Sample size was 54. And if you run that through your calculator under t-test, you would actually get something like this. When rounded to 2 decimal places, you get negative 2.36. And that's a complete step 3. Step 4. That same output from the t-test also gives us a p-value. And that p-value comes out to be 0.011 when rounded to 3 decimal places. And let's see here. We're going to draw this picture. Well, what kind of drawing do we need? Do we need a bell shape or one that's skewed to the right, starting from 0? Well, the test that determines that. Z-scores. Z's and T's are bell shape. Chi-scores and F's start from 0 and are skewed to the right. So we have a bell shape here since we're dealing with the Z distribution, where 0 is at the center. Our test stat is negative 2.36. That's somewhere around here. It's negative 2.36 standard deviations away. And this is a left-tailed test because we're looking at the alternative, and they're telling us that we shade to the left, and the area of our shaded region is the p-value. We're going to make our decision. And the decision is made by comparing your p-value to your significance level. P-value is 0.011, that's 1.1%. Compared to 10%, well, that's definitely less. And if it's less than the significance level, then we are rejecting the hypothesis. Okay, if you recall, what does that mean? What does a p-value mean? It just means it's the probability of making a type 1 error. Again, a type 1 error is one in which you reject the null hypothesis when it was actually true. Okay, you don't want to make that error. You shouldn't have enough evidence to reject something that's actually true. And the probability of that in our case is 1.1%. We were willing to be up to 10% chance of that being the case. Since it's less than that, then we're okay with making this decision to reject the null hypothesis. Step 6, we're going to come up with the conclusion statement. And we say that, well, if we go through that flow chart again, the alternative was the claim. We rejected the null hypothesis, so our data did support the claim that it was less than 200. Okay. The population mean of all such employee weights is less than 200 pounds. This next question is on hypothesis testing, but for two populations. Okay. So be prepared on the test for there to be two proportions, two means, mean difference, right? That's a matched pairs example, or two standard deviations. We'll just be using an F distribution for that, if you recall. That's a two-sample F test. Again, look at your notes for all the details on how to do these. Okay, they're all pretty much similar. It's all the same 6 steps. It's just different test stats, of course. Number 7. A marketing survey involves product recognition in New York and California. Of 558 New Yorkers surveyed, 193 knew the product, while 196 out of the 614 Californians knew the product. At the 5% significance level, test the claim that the recognition rates are the same in both states. Okay, so what's the claim statement? That'll give us an idea of what type of parameter we're dealing with here. Test the claim that the recognition rates are the same in both states. Recognition rates. Okay, what's a recognition rate? Was that a mean, a standard deviation, a mean difference, proportion? Well, the word rate means something per something, so that's a proportion, definitely. Okay, so they're just interested in whether the recognition rates in both California and New York are the same. So do the same percentage of Californians recognize this product as the same percentage of New Yorkers recognize this product. Okay, that's what they mean by that. All right, let's start where we always start. Step 1, our hypothesis statements. And we're dealing with two proportions, so P1 equals P2. And let's go ahead and call New York 1 and California 2. And the alternative, again, the recognition rates are the same in both states. Okay, so if they're the same, that means they're equal, right? So this is the claim statement already. Okay, and the alternative here would have to be that they're not the same, which means not equal. So this is going to be a two-tailed test. So these are typically harder to pass because you have to pass it on both sides of the distribution. Step 2, significance level, I believe they said, what, 5%? Yep. Step 3 is our test stat. We're dealing with two proportions, so this is going to be a Z test. It's going to be called 2-prop Z test. Okay, there's a pretty long formula for that. I'm not going to write it out. But the inputs on your calculator are going to be X1, N1. That's for the first sample. That'll be for New York. And for California, it'll be X2, N2. And if we could just read those off the problem, New York, 558 New Yorkers, so that's your sample size. Of those, 193 recognize the product. And in California, there's 614, and of those, 196 recognize the product. Okay. And if we put all these inputs into your calculator correctly, you're going to get a test out of 0.97. So that's about 1 standard deviation away. Step 4, again, that same output from the 2-prop Z test will also give you a p-value, and the p-value in this case is 33.3%. So because it's a two-tailed test, this 33% is actually distributed into the two tails, so it's about there's about 16 point something percent in each tail. All right, 0 at the center. We have 0.97 is somewhere around here. Because it's a two-tailed test, we also need its opposite, negative 0.97, and we're going to shade the tails. All right, and the p-value represents the total area here. So it's split amongst both of those tails. All right, so again, the probability of us making a type 1 error if we were to reject the null hypothesis is 33.3%. That's a pretty large chance of us making an error, right? 1 in 3. We're not willing to make that decision to reject the null hypothesis. It's too high. How do we know it's too high? Well, it's larger than the significance level, right? That's what step 5 is all about. We make a decision by comparing the p-value to your significance level. P-value is 0.33. That's definitely greater than 0.05, and we fail to reject the null hypothesis. Step 6. So in our case, the claim was the null hypothesis. We failed to reject. In our situation, we can essentially say that our claim is still true, right? But we don't really ever say it that way. Instead, we say there is not sufficient evidence to warrant rejection of the claim. And what was that claim? That the recognition rates are the same in both states. In this next question, be prepared for one of the following types of hypothesis test, and that is the goodness of fit test, test for independence / homogeneity, or an ANOVA test. That's when you compare 3 or more means. Okay. All right. So in this particular case, it says perform the indicated goodness of fit tests. Okay. So they already tell us what it is, but again, be prepared for any of the other ones listed above. Be sure to show the expected frequencies. Using the data below and a 5% significance level, test the claim that the responses occur with percentages 15%, 20%, 25%, 25%, and 15% respectively. So essentially these all correspond to these letters. Now there's no real context to this problem other than we have some observed frequencies of whatever the situation is, and then we have values that we're expecting to see. Okay, so this is our raw data, and what we expect to see, that always comes from the null hypothesis, really. Okay. All right, so let's go ahead and start where we always start, and that is our hypothesis statements. Null hypothesis and alternative. For a goodness of fit test, we're looking at the claim statement here, and that claim statement is test the claim that the responses occur with percentages 15%, 20%, 25%, 25%, and 15%. Okay. So we say that we're going to call, like, A is going to be 1, B2, C3, D4, and E5. So we'll just call it, I'll just put numbers next to these. I'm just going to get a little cluttered there. It's just for naming purposes. So I'm going to say that the proportion for that first response, they're expecting 15% for that. You can probably think of this as maybe some sort of question where there was 5 choices, and they expected that people will respond A with 15%, people will respond B with 20%, and so on. Now another version of this type of question is if they all have the same frequency, like a fair die, then you would just have P1 equals P2 equals P3, and so on. But this was more of a, each response actually has a specific percentage. Okay? And the alternative, at least one of these has to be off. So you would say that at least one proportion is different. 2, identify our significance level. I believe they told us it's 5%. 3, and that is our test stat. Okay. For goodness of fit test, we're going to be using the goodness of fit test in our calculator. Again, if you have a TI-83, review the notes, and I do show you how to calculate this goodness of fit test stat and the p-value in an alternative way. But for those of you with the 84, you have this already built into your calculator. All right, so that test stat, if you recall, it's the sum of each observed value minus the expected value for that category. Square that and then divide it by the expected count. Okay, so we need to have observed values, which we already know. It's at the top of that list. It's at 12, 15, 16, 18, 19. And the expected count, well, how do you go about calculating those? Well, let's actually use the space off to the left here to actually come up with those. Expected counts are n times p1. And since they're all different, I'm going to have to calculate this for each proportion. There's 5 of them. Okay. And what would n be? Well, you would have to actually sum total everything here, right? If you get the total here, add them all up, that'll give us n. That's the total number of observations, right? The sum of the observations. And 12 plus 15 plus 16 plus 18 plus 19 actually gets us to 80. All right. So if for the first response A, we expect there to be 15% that are responding A, well, 15% of 80, well, what's that? 80 times 0.15, we get 12. Okay. Let me move this to the side here. Okay. And same thing here. 80 times, well, for P2, look, I'm looking at the null hypothesis. Here, I'm looking at these guys right here. That is 0.20. And 20 times that, 16. Then we have 80 times 0.25. That's 20. P4, that's 80 times, again, 0.25 again, so it's the same calculation, 20. And of course, the last one, it'll be 15%. We've already done the calculation for E1. And that came out to be 12. Now the sum of all the expected values should also be the sum of all the observed values, right? The sum of the expected should be the sum of the observed, right? Which all equals n. So n is 80, the observed counts as 80, and if you count these 4 numbers here, 5 numbers here, this should also give us 80. Okay, and that's how you would check. So let me go ahead and write these in. 12, 16, 20, 20, and 12. Okay, now what we observe and what we expect don't always have to be the same, right? That just means it doesn't fit well. But sometimes they do fit pretty well. Like for example, A here, it's right on the money. What we expected and what we observed was exactly the same. The only ones that seem to be kind of off by a lot is, I would say, E here, right? 19 versus 12. But everything else seems to fit pretty nicely, right? And just by the looks of it, I wouldn't say that it doesn't fit well. I would say that what we observed and what we expected seems to be in line with each other. But to just be sure, of course, that's why we run these tests and come up with the p-value. So if we run this test in chi-squared GOF, well, we have to put this list into L1 and L2. And what I'm going to do, it doesn't really matter as long as you identify them correctly. I'll put this one in L2, L1. The order really doesn't matter, especially if you're using the function in your calculator. But if you're using a different function, one that I would give you through, I believe, Math 200A, it requires this order, so I'm going to just stick with this order. Okay. And let's actually do this one on the calculator. Let me actually go through this one. Okay, here we are at the calculator, and what I'm going to do is put these 2 lists into my calculator under Stat, Edit, clear out the list here. And I said in L1, I'm going to put all the expected values. So it's 12, 16, 20, 20, and 12. And in L2, I'm going to put my observed values. Let's go ahead and jump out of this so I can quit. And I'm going to go to stat again, go to tests. Again, if you have a TI-84, you should have this test in your calculator. If you have a TI-83, again, go through the notes and follow the instructions on how to actually come up with the test and the p-value for that. Okay, chi-squared GOF test, that's the one we're looking for. And my observed is in L2 and my expected is in L1. Just make sure that's lines up with what we have. Your degrees of freedom. Now your degrees of freedom is always the number of categories minus 1. All right. How many categories do we have? Well, the categories were the responses here, A, B, C, D, and E. That's 5 categories. 5 minus 1 is 4. So that's 4. And let's go ahead and calculate. All right. So my test stat here, my chi-squared is 5.146 if I'm rounding to 3 decimal places. I'll just round it to 5.15. And your p-value is about 27.3%. That means we're not going to be able to reject the null hypothesis. And what's the null hypothesis? That it follows that 15, 20%, 25%, 25%, 15% distribution, right? And that's, I had already expected that because what we expected and what we observed wasn't too far off from each other, so it's hard to completely reject the null hypothesis. All right, so we have 5.15 as our test stat here. That's a complete step 3. Step 4, we're going to need a p-value also from that calculation. That one was what? 0.273. What kind of picture are we drawing? Well, for a chi-squared, anything that's chi-squared or F distribution follows a skew to the right distribution graph, starting from 0, something like that. And we have, well, the 5.15, it has, these are always going to be right tail tests, first of all. So the area shaded to the right will represent this 27.3%. Okay, so we have to draw this test stat of 5.15 such that the area to the right of that test stat is 27.3. So I would say the 50% mark is like around here. So I don't want it to be there. I want it to be maybe around here. So such that this area here represents about 27.3%. Okay, that's a complete step 4. Step 5, we're going to make our decision. And we had already discussed that. Our p-value versus our significance level. P-value 27.3 and our significance level of 5%. P-value is greater than that, so we're going to fail to reject the null hypothesis again. Okay, so if we follow that flow chart like before, our claim, oh, actually I didn't identify the claim. Our claim was this, right? This is our claim statement. That's why it's important to identify that early on. So that matches up with the claim statement. We weren't able to reject that. So in a sense, the null hypothesis is still true. But we don't say it in that way because we can never really claim that something's true. We just don't have enough evidence to reject it. Okay, so that's what we're going to say. There is not sufficient evidence to warrant rejection of the claim that the responses occur with the stated percentages. That's how I would say that instead of writing it all out.